In this video, we'll look at an example of a continuous probability model. Let's look at problem number 7. What we're measuring here is the time to finish the maze, and it is a lab rat that's going to finish the maze. What we're doing is measuring time. Measurement of time is continuous, and it could take anywhere from 0 to any number of minutes, which means you can go anywhere from 0 to infinity. Every single number on the right side of 0 counts. You can include 0 if you want to, and it goes from 0 to infinity. So every single number starting from 0 counts. So this is a continuous sample space. Individual outcomes cannot be listed, and that's why we use the interval notation to represent the sample space of this particular experiment. Problem 9. We randomly choose any real number between 0 and 1. So it's any real number between 0 and 1. It could be 0.25, it could be 1 over, let's say, 2 radical 2. It could be just any number between 0 and 1. So every number between 0 and 1 is equally likely to be selected. Now all numbers from 0 to 1 cannot be listed. It's uncountable, and it's impossible to list the set of numbers, so we have to use the interval notation to represent this sample space again. So the sample space is anywhere from 0 to 1. So anything in that range of values is our sample space S. So this is again an example of a continuous a probability model or a continuous sample space. Now in a discrete sample space, it is possible to isolate outcomes, individual outcomes, and find the probability of an outcome. But in a continuous model, it is impossible to isolate one single outcome and find the probability of it. It doesn't even make sense. What we do is, instead of finding the probabilities of individual outcomes, we look at small subsets of that sample space. So for example, 0 to 1 is our sample space, and we could, for example, say what is the probability of selecting a number between 0.5 and 0.75. So we're looking at a small piece of the entire sample space, which is from 0 to 1. So what is the probability of that happening? Or we could say, for example, what is the probability of getting a number between 0.5 and 0.51. No matter how small the line or the segment or the piece of the subset is, you can still do it as long as it is a range of values starting from 0.5 to 0.51, for example. The probability density curve is just like a histogram, and we look at the shape of the histogram. Sometimes it could be a bell-shaped distribution, sometimes it could just be a rectangular distribution. It all depends on what shape the histogram forms. So that is the probability density curve. The minute we call it the probability density curve, what we're going to assume is that the area under the curve is equal to 1. So that's the total area under the curve. So the total area under the probability density curve is always equal to 1. That's the important thing to remember. So question number 10. It says that a random number generator will spread its output uniformly across the interval 0 to 1. So basically a random number generator, what it does is it continuously generates numbers between any two given numbers, and we can make a note of all the numbers and then collect a long list of such numbers generated by a random number generator and make a histogram out of it. So when we make a histogram, for example, if we are generating numbers between 0 and 1, then what we're going to get is, so we have all numbers from 0 to 1, and then we divide it into intervals. So let's say 0.0 to 0.1, 0 to 0, 0.1 to 0.2, 0.2 to 0.3, and so on, and we can make intervals, and then each of these numbers that is generated by the random number generator falls into one of these intervals. So for example, if it is 0.225, it falls between 0.2 and 0.3, and we collect lots and lots of numbers and then make a histogram out of it. Every number is equally likely, so there is no reason why there'll be more numbers in a certain interval than the others. So if we have generated enough numbers, then more or less your histogram of this particular experiment is going to look like this. All numbers are equally likely, that's why the frequencies of all the numbers will be more or less the same. So basically what we get is a rectangular distribution. So we have 0 to 1 as the base, and the shape of the distribution looks like a rectangle. But the important thing about a probability density curve is the total area under the curve is equal to 1. So if you think about it, the base is 1, the area is 1, so area is equal to base times height. So if the area is 1 and the base is 1, then clearly the height would have to equal 1. So now we know all the dimensions. The height equals 1, the base equals 1, and the area equals 1. Fine. Previous slide, the shape of the histogram is a rectangle because all numbers are equally likely, so each bar will have the exact or more or less the same height. And if we generate enough numbers, this is what the distribution, the shape of the distribution will look like. So the base is from 0 to 1. We know that a probability density curve, the area under the curve is equal to 1. Since the base equals 1, our calculations here show that the height is also equal to 1. So area equals base times height. So if area is 1 and the base is 1, then we plug in the values. The height is x, the unknown. X times 1 is x, and x is equal to 1. So now the height is also equal to 1. So this is an important calculation because we're going to use this rectangle to find the area under the curve. And why we care about the area under the curve is because in a continuous model, in a continuous probability model, the probability of an event is equal to the corresponding area under the curve. So for example, if I say what is the probability that a randomly selected number falls between 0 and 0.5, then I'm just looking at the area of this rectangle, which gives me the probability. So important thing to remember is we need to know what the density curve looks like for a continuous probability model, because the probability of any given event corresponds to the area under the curve corresponding to that particular event. So for example, if we want to find the probability that a number lies between 0.8 and 1, we need to look at the area of this rectangle, and the base here would be the distance from 0.8 to 1, which is 1 minus 0.8, which is 0.2. So 0.2 times the height, which is 1, that would be the area. So area equals probability. So 0.2 is the probability that a randomly chosen number between 0 and 1 falls between point 0.8 and 1. Now the next question is, find the probability that a randomly chosen number x lies between 0.5 and 1. So in a continuous probability model like the one we are just looking at, the probability of any event is the corresponding area under the probability density curve. So let's look at the area that corresponds to picking a number between 0.5 and 1. So there is, let's say, 0.5. So picking a number anywhere from 0.5 to 1 is that base. So then we are looking at the area under the curve, which would be this rectangle. So the base is 1 minus 0.5, which is 0.5, times the height, which is 1. So 0.5 times 1 is 0.5. So the probability of picking a number between 0.5 and 1 is 0.5. What if we had to pick a number between 0 and 0.5? Notice that that's just the other half of the curve. So that would be the area of the dotted, you look at the dotted part of the curve, that's the area that we're looking for, and that is also equal to 0.5. Because the base is 0.5, the height is 1, multiply the base with the height and it's equal to 0.5. So finding probabilities in this particular type of problem, where the probability density curve is just a rectangle, it boils down to finding areas of rectangles. As long as you know the height of the rectangle, we can figure out the base and multiply the two to get the area, which is also equal to the probability. So look at the next problem. Find the probability that a number lies between 0.8 and 1. So now let's look at the probability density curve between 0 and 1. Now let's see what area corresponds to this event, picking a number from 0.8 to 1. So 0.8 to 1. That's the base of the rectangle, 0.8 to 1. So you go 1 minus 0.8, which is 0.2. So that's 0.2. That's the base. The height we've figured out is equal to 1. So the area of the rectangle is equal to 1 times 0.2, which is equal to 0.2. So the area is equal to probability. So probability of picking a number between 0.8 and 1 is the same as area, which is corresponding to that event, and that's equal to 0.2. The probability that we need to find next is the probability that a number lies between 0.5 and 0.6 or 0.8 and 1. So let's look at the two events. So this is our probability density curve because we're picking a number between 0 and 1. So our base is 0 to 1. 0.5 to 0.6. If this is 0.5, let's say this is 0.6. So that's the area we're looking at if we're trying to figure out the probability between 0.5 and 0.6, picking a number between 0.5 and 0.6. And then the other event is picking a number between 0.8 and 1. So that's the rectangle, that's the other rectangle. Notice that these two events do not overlap, which means if you're trying to find the probability that a number lies between 0.5 and 0.6 or the number lies between 0.8 and 1, we just need to add the two probabilities because there is no overlap. We just add the two individual probabilities to get the probability of that combined event. Finding probabilities is just finding areas of rectangles. All we need is the base. Just subtract 0.5 from 0.6. to get the base, and then multiply it with the height, and that gives us the area. So that is the probability that a number lies between 0.5 and 0.6. For the other event, a number lying between 0.8 and 1, we've done this before. The base would be 0.2 multiplied with the height, and we get 0.2. So adding the 2, we get 0.3. The addition comes because of the word or. What's the probability that a number lies between 0.4 and 0.7? Now you get the idea. It's just the area of the rectangle corresponding to that event. A height is fixed. The height is always equal to 1. The base in this case would be the difference between 0.4 and 0.7, which is equal to 0.3. Multiply the base with the height to give you the probability of that event. Notice that the previous problem we picked a number between 0 and 1. So we looked at the histogram, and then the shape of the distribution was a rectangle. By theory, we know that the area under the curve has to be equal to 1 because the probability, total probability of the sample space is equal to 1. So the first thing we did was figured out the height, and we said the height has to equal 1 because 1 times 1 equals 1. The base is 1, height times base equals area, which is 1. Now what if we were picking a number between 0 and 3 instead? So again, if you're picking a number between 0 and 3, we'll have a random number generator pick multiple numbers, and then we make a histogram, and if we've picked enough numbers using the random number generator, then the histogram should look like a rectangle again, because every number is equally likely. There is no reason why there should be a difference in the heights of the bars. So we know that the total area again equals 1. So the total area equals 1. In this case, the base is equal to 3. Now all we need to do is figure out the height, and we'll be able to do any sort of calculations of probability once that is done. So area equals 1. The base is 3 in this case, because now we're picking a number between 0 and 3 instead of picking a number between 0 and 1. So the base is 3. We need to determine the height of this rectangular distribution. Area equals base times height. We just plug in the numbers. Area equals 1, base equals 3, height we call it h. Solving for h by dividing both sides by 3, we get 1/3 equals h. So the height of this distribution is 1/3. So now if we have to find the probability that a number lies between 1.1 and 2.9. So let's say that is a 1, that's a 2, and that's a 3. So 1.1 is somewhere here. So 1.1 and 2.9, it's somewhere here. We have to find the area of this rectangle with base that extends from 1.1 to 2.9. So we got 2.9 minus 1.1, which is equal to 1.8. So that is the base of the rectangle. We've already determined that the height is equal to 3. So we divide the base. So we've determined that the base goes from 1.1 to 2.9. The height we've already determined is equal to 1/3. The area gives us the probability. So area is base times height. So the base is the difference between 2.9 and 1.1, which is 1.8, and then times height, which is 1/3. So basically 1.8 divided by 3, because of the 1/3, 3 is in the denominator, so we divide by 3, gives us 0.6. So 2.9 minus 1.1 divided by 3 is equal to 1.8 divided by 3, which is equal to 0.6. So the probability of selecting a number from 1.1 to 2.9, assuming that we were picking numbers between 0 and 3, would be 60% or 0.6.